Hello everyone, my name is Mark and I'm going to give you a short introduction to XAutoML, a visual analytics tool for establishing trust in automated machine learning. AutoML aims to automatically construct complete machine learning pipelines given only an input dataset and a loss function. Domain experts that have no expertise with data science, machine learning or statistics are enabled to construct ML pipelines without the help of a data scientist. Alternatively, AutoML can also be used by data scientists to automate tedious tasks like hyperparameter optimization. Even though such automatically synthesized ML pipelines are able to achieve a competitive performance, recent studies have shown that users do not trust models constructed by AutoML. In the last 10 years, various automated machine learning systems have been proposed to build end-to-end machine learning pipelines with minimal human interaction. Yet current AutoML systems behave in a take-it-or-leave-it manner without providing sufficient information for users about the optimization procedure or the resulting ML pipelines. Without sufficient information, users cannot make an informed and accountable decision about whether an ML pipeline created via AutoML should be used at all. We propose XAutoML, an interactive visual analytics tool for explaining arbitrary AutoML optimization procedures and ML pipelines constructed by AutoML. XAutoML combines interactive visualizations with established techniques from explainable artificial intelligence to make the complete AutoML procedure transparent and explainable. In this example, we will use XAutoML to visualize an optimization run from AutoScaLearn, but other AutoML libraries are also supported. We use the credit G dataset in this example. First, we split the dataset into a train and test set. Next, we will use AutoScaLearn with the default configuration to search for a model with the best possible accuracy for 10 minutes. After the 10 minutes have passed, we load the optimization results in XAutoML. The visualization is directly rendered in Jupyter. On the left-hand side, we can find general statistics about the optimization, like the total number of evaluated candidates. Down below, a scatter plot of all candidates over time is given. In the middle, we see the candidate leaderboard. For each evaluated candidate, the performance, prediction time, and a preview of the constructed pipeline is displayed. We can check further aspects of a single candidate by expanding it. Each of these cards contain information about the candidate concerning a specific topic. For example, the performance details cards displays the performance regarding different metrics and a confusion matrix. Using the global surrogate card, users can fit a decision tree with varying complexity to the selected candidate to understand its behavior. The content of these cards is always computed on the output of the currently selected pipeline step. At the moment, a virtual data source node is selected. We can, for example, inspect the output of each pipeline step using the dataset preview. By selecting a pipeline step, the current dataset preview is updated. We can use these Continue in Jupyter buttons that are scattered throughout XAutoML to export information to Jupyter. Clicking here, a new Jupyter cell is generated which returns the current intermediate dataset. We can use this option to gain more insights that are not directly available in XAutoML. The remaining cards contain information about the importance of available features, selected hyperparameters, and hyperparameters importance. Besides validating single candidates, it is also important to understand what happened during the AutoML optimization. In the Search Space tab, we can find information about the actual search space and search strategy. We can use this structure search graph with this time-lapse slider to observe how different pipelines are constructed over time. In the hyperparameter optimization view, we can inspect the hyperparameters of each ML primitive. Each axis down here represents a single step in a pipeline. We can expand each step to reveal the used ML primitives in the step. By selecting a single ML primitive, we can check the hyperparameters of this algorithm. In the current view, we can check which hyperparameters were chosen during the optimization, but we don't know which strategy AutoSQLearn used to sample the actual values. We can click on any hyperparameter to see how the values were sampled over time. In this case, it is hard to extract a search strategy from this view, as only a few configurations were sampled. The optimization progress view on the left-hand side helps users to decide if the optimization duration was long enough. All candidates are mapped into a two-dimensional view with similar candidates having a smaller distance. In this plot, we can see that all evaluated candidates are scattered quite evenly and no local cluster has formed. This is an indication that the optimization duration of 10 minutes was too short. Finally, we can inspect the ensemble constructed by AutoSQLearn. The top card contains the same inspections as in the leaderboard for the individual candidates, but this time for the complete ensemble. In the ensemble overview, all ensemble members are listed on the right-hand side. We can select any record from the dataset on the left-hand side to check the individual predictions of all ensemble members. In the last plot, the decision surfaces of all ensemble members are plotted. We can use these plots to get a rough idea how each ensemble member behaves. If we want to get more details about a single member, we can directly jump to the corresponding details. If you would like to try out XAutoML yourself, you can head over to GitHub and give it a try. You can find the link in the description down below. Thank you for listening.